to rewatch this lesson, they can do that. Is everybody ready? Let's do number 6. And it says, calculate the mass of silver needed to react. I'm sorry. How many liters of carbon monoxide at STP are needed to react with 4.8 grams of oxygen to produce carbon dioxide? Wow. Okay. Good news. They already gave me a balanced equation, right? All right, so anytime, I know it's Monday morning, but you cannot do any kind of stoichiometry without a balanced equation. So can everybody remember that? You have to have a balanced equation to start with. All right. All right, ready? All right. What's the only information they gave us on number 6? What's the only information right here?
4.80.
And notice where I put it. Where did I put it? I put it here. Why didn't I put it down here? What do I put down here? Moles. I always know that I can find moles down below it. So I don't put anything that, if it's moles, it goes down here. Anything else goes up here. Now, they want to know how many liters of carbon monoxide. Whoa, liters? How's that? I don't remember doing that yet. You haven't? Okay, so here's what we're going to do is, let's go ahead and find out, let's find out this. Let's find out this, and then we'll be ready to go up here. Ready? Do you remember how to do this? I know it's Monday morning, but what's the, we'll do the long cut, then we'll do the shortcut. Okay, 4.8 grams of oxygen. Is that the given? Okay, and what do you want to, if you'll say it in words, what do you want to change? Say grams of oxygen to what? Okay, so what label has to go away? And you want moles of oxygen, right? Okay. And so what do you know about, remember last chapter, the 3 equivalents? What do you know about O2?
32.
1 mole of O2.
32.
1 mole of O2 is what?
32.
Right? Now, let's see if you remember the shortcut. We're going to do it both ways. When you want to go down in the mole world, you what? You divide by molar mass. Now, the biggest mistake people make with the shortcut, when I go up or down in the mole world, I do not look at coefficients. The only time I look at coefficients is when I go sideways in the mole world. So right now, I'm just going down. So let's do the long cut method, and then we'll do the shortcut. What's 4.8 divided by 32? What do you have, Ben? You got the $5 calculator.
0.015.
Point zero what?
Or no, 0.15.
Oh, 0.15. Okay. Is everybody getting 0.15? Okay, so let's put that here. Okay, now, I shouldn't have done that. I shouldn't have written that there. Sorry. Okay, now, let's go sideways. In words, what are you doing here? What are you changing from what to what?
Moles to moles.
Moles of what?
Oxygen.
Moles of oxygen. Change it to moles of what? Okay. Well, I wish I knew where you get numbers for this. When you go sideways in the mole world, where do you get the numbers?
Coefficients.
What do you think, Sean? That's right. Okay, so take a look. It says here for every 1 mole of O2, it'll produce 2 moles of that. There we go. Isn't that right? Now, what was the shortcut on this? Watch this. Shortcut. When you're going sideways, look at the coefficients. 1, 2. Gotta get bigger. Which fraction is going to make you bigger? Multiplied by 1/2 or 2 over 1? This number over here has got to get bigger. 1, 2. What are you going to multiply by? 2 over 1, right? All right, so what's this number here? Is this 0.3?
Yep.
Okay, we're almost there. All right, so let's say I wanted to know how many grams of carbon dioxide. What if I wanted to know how many grams of carbon dioxide? What would I do? What would the shortcut be? If you don't get down the mole world, you divide by molar mass. But what if you want to come up out of the mole world? What do? You multiply by molar mass. Does anybody know the molar mass of carbon dioxide? What's the molar mass? Yeah, very good. Very good. So let's do a shortcut. What's 0.3 times 44? Let's do grams here, just to play a game here. What's 0.3 times 44? 13, how much?
13.2.
13.2. Okay, now, if they had asked me grams of carbon dioxide, I've been done. So what's the new lesson today? What is the new lesson today? It has to do with gases. There were two people involved with the mole concept, and one person's name is hyphenated named Gay-Lussac, and the other one is Avogadro. Now, they both figured out that with gases, a certain volume of one gas would react with one or two volumes of another gas. So all this was done with gases. So here's what happened is gases, okay, here's my problem. Do you know what happens in a little balloon if you heat it up just a little bit? If you just put I'm from Indiana, and we played basketball all the time. It didn't matter. If it was in the winter, we'd shovel off the driveways that had snow all the time, and we played basketball. We just played Indiana. It was big basketball. A lot of Indiana basketball came to North Carolina. As a matter of fact, a lot of that, there's a big connection there. So everybody knew that when you got ready to play basketball, you would get mad. You get mad at the person. Hey, we came to your house to play basketball. You left the ball out all night. And so what happens? It's cold. It doesn't bounce. What you're supposed to do is leave the ball in the house, right? And just heating that ball a little bit makes the gases expand, doesn't it? And that's what makes the ball work so much better. All right, so for gases, if you are not careful about the temperature or the pressure, a gas can take up this much space or this much space. So you'll hear this term called STP. Okay, now STP in chemistry means standard temperature and pressure. Now, don't let that bother you because that's not the big part of the lesson. Scientists had to figure out, hey, if we're going to compare gases with gases, you can't have one at one temperature, one another. So they decided, and you don't even have to know this, but 0 degrees Celsius and 1 atmosphere of pressure. You say, what the heck is 1 atmosphere of pressure? If I went to the beach and I was at sea level, the amount of pressure I would feel by the air is called 1 atmosphere of pressure. Did anybody here scuba dive? Anybody ever done any scuba diving? You have? Where? Where is it? Okay, now, did they give you a lesson? Okay, you had, because normally they don't let you put on the stuff unless they give you a little lesson, right? Did they, I don't know how much, was it a half-day lesson or a long, many lessons? Okay, so the half-day lesson, they just don't want you to kill yourself, right? So they probably told yourself, don't hold your breath when you come up. Did they tell you that? Okay, so here's another thing they could have told you. Wait, I lost my train of thought. Scuba diving, that's right. For scuba diving, if you go down about 33 feet, all right, you're going to feel twice the pressure you did at sea level. So right now, there's a certain amount of pressure on my body. If I go down 33 feet of water, that's the same weight as all the air on top of my head. Now I'm under 2 atmospheres of pressure. You get that? And did you remember that when you went down, did you feel pressure? Okay. So anyway, 1 atmosphere of pressure is the simplest way of telling you about pressure. It's the same pressure you'd feel at sea level, okay? So I'm not worried. I'm not going to spend a lot of time on STP. Whenever you see STP, I will tell you, here's what we got here. I'm going to tell you something about carbon dioxide. 1 mole of carbon dioxide, and this is something you already knew, is 6.02 times 10 to the 23rd. And why did I put molecules? Why did I put molecules after CO2 here?
Because it's...
What, isn't it a compound? Isn't it a compound? Is it a non-metal? Okay, that's why I put molecules. Equals 44 grams. And now, watch. I have one new equivalent for you. A new one. It's right there. You see that blue box? See that blue box? Over there? Okay. See it says STP?
22.
Okay. They figured out that 1 mole of any gas, it didn't even matter what kind of gas it was. 1 mole of any gas, oxygen, carbon dioxide, nitrogen. 1 mole of any gas takes up how much space?
22.
22.4 liters. And by the way, that box, this box right here is a liter. You know what a liter is, right? A 2-liter bottle. That's 22.4 liters right there. Okay, I'll leave that box up here. Every time you take a test or quiz, there it is if you need it. So what's my lesson? All I want you to do is add a new equivalent if it's a gas. Okay, so now, ready? Let's start here with my given. Let's say 0.30 moles of CO2, and I want to change it to what? What's the problem say? It says, how many liters of carbon monoxide? Oh, did I do carbon dioxide? Darn it. Darn it.
But the equivalent is just.
I'm sorry. All right. Can we go over here? What do they want me to find? They want not carbon dioxide. What do they want? I'm sorry. I tell you what. We'll do carbon dioxide first, then we'll do carbon monoxide. How about that? All right, ready? What do you know about carbon dioxide? I know that 1 mole of carbon dioxide is the same as what?
13.2.
Okay, so tell me how many liters of carbon dioxide are going to be made? How are we going to do it? All right, need a hit on the calculator. Who's got it?
302.4.
Say it again.
302.
22 times 0.3. It's going to be about 8 something, isn't it? Not 8, but 6.
6.72.
Okay. Okay. I made a mistake. Instead of doing carbon monoxide, I did carbon dioxide, but let's go ahead and do it. How would we do this one? Hey, by the way, what's the shortcut? What's the shortcut? Moles times 22.4 gives you liters, okay? So now, can we find out what this box is over here? Let's do shortcut. What do you think? Look at this right here. 2, 2. Matchy, matchy. What do you think? Oh, look at that. What a coincidence. So what's 0.3 times 22.4? So 0.3 moles of carbon monoxide, 1 mole of carbon monoxide equals 22.4 liters. So we get the same number. What do you think? Okay, I made a mistake by doing carbon dioxide, but do you understand how that works? Let's say I want to have liters of carbon monoxide. What do you have to get into before you can do it? Don't you have to get into the mole world? So let's just say that that's my given right there. And I want to change moles of carbon monoxide into liters, and that's how we do it right there. Now, I mentioned this last week. You're really not a very good student if all you're doing there is sitting copying what I put. Really, I'm sorry. You maybe you pat yourself on the back. Hey, I copied everything you put down there, right? That's nothing. It's nothing. How about some questions? Anybody have some questions they want to ask? You have a question. You have a question? You sure? Luke, you have a question? Do you know how I got? Does everybody know how I got this?
Yeah.
All right. Now, how do you go from moles into liters? Right there, right? Everybody okay on that? So you have a new equivalent if it happens to be a gas. You can't use it unless it's a gas. All right. Wait. So number 6, the answer will be 6.72 liters of carbon monoxide. There we go. All right. So now let's have you do number 7. I want you to sit with somebody. Sit next to somebody, and I want you to do number 7. Calculate the number of liters of oxygen needed to produce 15 liters of dinitrogen trioxide. All right, I'll help you out a little bit. Boy, it's nice they gave me the balanced equation. All right, 15 liters. Okay, that's what they give me. And they want to find out the number of liters here. Hey, can we go from liters to liters? What do you think?
Yeah.
No, there's a tree in the way, remember? So what's our plan? What's our plan? Go down the moles, over the moles, back up. All right. All right, sit with somebody. All right, I'll have you do it for about a minute or so, and if you're having trouble, I'll help you. I know it's Monday morning, but I'm hoping this stuff stayed with you from last week. Okay, now look at somebody else's paper and say, "Hey, what? Hey, how'd you do that? How'd you do that?" Does everybody see the plan? Change liters of nitrogen, dinitrogen trioxide. Change liters into moles. Go from moles of that to moles of that. And then pop up into liters. Okay, now some of you have not partnered up yet. Does that mean you're doing it by yourself? Does that mean you don't know what you're doing? That's okay. I'm okay if you struggle a little bit. You should have to struggle a little bit. And then when you come up with it, you'll say, now I know how to do. Now I know what to do.
Whoa, how'd you do that? It's right there.
Talk to each other, okay? You want to talk to each other. You give up. We just started. We just started. Okay.
Well, it tells you 15 liters.
Did you do the like right here?
Yes, that's the given, isn't it?
It tells you, and then to get from liters to moles.
Oh, is it, we would do two.
Ooh, you're going to use that blue box, aren't you?
You just put 15 liters, and then you put 22.4, because that's what that is, and then as 1 mole. 45 over 2. And then you get that, and you just gotta get that. And then they put 22.5.
You do 15 times 3.
I'm really proud of you. Some of you are getting ready to give up, and you stayed with it. Stay with it. Talk to somebody. So one mole of any gas takes up 22.4 liters of volume. All right, so are you done giving up? Can you start back?
Yeah, I got it.
Okay. All right. See, it makes you feel good when you figure it out, when I don't tell you. Talk. You guys talking? Okay. Aiden, you talking? Are they doing the right thing? Check them, see if they're doing the right thing. Check Zach. Hey, talk to Zach. Talk to Zach, see if he's doing the right thing. Are you guys done? Wow. Very good. Did you guys finish? Okay, get in. All right, 30 seconds, and then I'm going to tell you how to do it. In 30 seconds, I'm going to tell you how to do it.
So you put that above it, and then to get to moles, 15, you replicate, and then you put 22.4 on the bottom. And it is one.
Make sure you have a good label. 22.4 what? Liters of. Okay, here we go. Now, if everybody would stop for a minute and look up here, and if you did what I'm getting ready to do, you just kind of shake your head. Oh yeah, oh yeah. And if not, you say, oh, that's what I did wrong. Okay, so it's one of these two things that are going to happen. Either you're going to shake your head, say, oh yeah, that's what I did. There it goes. Okay. All right, so I noticed that this is only given, and they want me to go over here, but I can't go from liters to liters, so I have to go down and across. So I say to myself, change liters of that into moles, get down the mole world. Now, what do I know about any gas? I know that 1 mole of any gas, including this one, takes up 22.4 liters. Now, how did I know that that was going to go on the bottom?
Because that's a cancel.
Because what label had to go away? Look up here. What label had to disappear? Liters. That's why I knew to put it there. Now, let's go ahead and give me that number. Somebody had
7.67.
7 point what?
67.
Start again.
7.67.
Did everybody get this or not? I don't want to move on if we didn't get that.
Or 7.6.
Do you divide 15 divided by 22.4? I don't think you're going to get that.
0.67.
Say it again.
0.67.
0.67. That makes sense. Did everybody get that?
I can't see the decimal on this.
Oh, you can't? Okay. All right, everybody stop. Stop, stop, stop. Shh, stop. Now, where are we going now? Say, I'm going to change moles of this gas into moles of that. So here we go again. What label has to go away down here? Moles of the N2O3. And I'm going to change it to moles of O2. And Sean gets tired of saying this, but I'll say it this time. When I go sideways in the mole world, where do I get my numbers? From the coefficients of the balance equation. It says here for every 2 moles of that, you'll get 3 moles of that. So, let's go ahead, and it's going to be about 1.5 times bigger than this. It's going to be close to 1, I bet, isn't it? What number do you have? Uh-oh, what do you have? Is it 1 exactly? About 1? Wow, that's interesting. Okay, and then my idea is I need to go up here, right? And I want to change moles of O2 into liters of O2. And what's that new thing we learned today? 1 mole of any gas takes up 22.4 liters of space. So what does this come out to be? Is it coming out to be about 22? 22 point what? Did everybody get that? About 22.5, 22.4, something like that. What do you think? Okay, so now, if you look at your homework, we've done a lot of them on the front page. You have to do the rest of them. Now I'm going to turn it over, and I want to show you the probably the hardest part of the chapter, but it is hard, but not hard. The hardest part of the chapter has to do with it says limiting reagent, and I'm going to show you how to do that, okay? Okay, so anyway, let me, if I could have your attention here, this is the last part of the chapter. It's the neatest part of the chapter. It's the highest level part of the chapter, but some of you will get this. And then tomorrow, all of you will get it. Some of you will get it today. So what I'm going to do is I'm going to start with something, something really simple. I'm going to start out with oxygen is going to react with hydrogen, and it's going to make water. So I'm going to pick a reaction that I know is pretty simple. Okay, can we balance this? Can everybody balance that real quickly? Now you have to switch now. This is not a homework question. We'll do a homework question based off of this, but we'll do this one here. So this is notes, and then we'll do a homework question. All right, how do you balance this? Who's J3? Tell me how to balance this. I have 2 on the left. Ooh, so now what? Yes. What about hydrogen now? So you got how many hydrogens? Is that it? What do you think? Okay, you can't do stoichiometry or that balanced equation. Now what I'm going to do is I'm going to make up a number. I'm going to say that I had 100 grams of oxygen, and that's my given. Now one more time, where did that come from? I just made it up. Everybody okay? Okay, now I'm going to give you also 100 grams of this. So what makes this problem look different? What makes it different is I told you how much of both reactants there are. Now that sets up a kind of a weird situation, okay? And I'm going to tell you how this works. Is it okay? Are you guys ready to use shortcut or not? Yeah. Okay, so what I'm going to do is I'm going to write some molar masses over here. Let's do some shortcut. What's the molar mass of O2? 32 grams, okay. What's the molar mass of H2? 2 grams. How about H2O?
18.
You're very good at this. You're very good at molar masses. Okay. Okay now? All right. So what I'm going to do here is, this is called a limiting reactant. Here's what it means. It means that, let me tell you a story. Let's make up a story. I'm going to make up a story. I haven't told this story yet about bread and peanut butter. Have I done? Okay, I'm done. Let's say, I'll pick somebody. Ben. Let's take Ben and Luke.
Pick Luke.
Ben and Luke. Okay, Ben. Anyway, yes. Yeah, okay. So Ben and Luke, hey, Ben and Luke, this Saturday, we're going to, we had a chance to do some volunteer work. And they said they needed some sandwiches made for the homeless shelter. We're going to make a whole bunch of peanut butter sandwiches. And so what we're going to do is, Ben, you got the next 4 days, and be very nice. Go find as many grocery stores as you can, and ask them, would they be able to donate maybe 1 or 2 loaves of bread? And then on Saturday morning, you're going to come with all that bread that you got. And then Luke, you're going to go and ask people if they could donate 1 or 2 jars of peanut butter, and you're going to bring all that. So we get the whole class. Somehow the whole class says, this is a great idea. We're all going to show up on Saturday, and here comes Ben. He has a truck, and he's got like about 200 loaves of bread. I couldn't believe it that he got that many loaves of bread donated. And so Ben's saying, oh, man, we are going to make so many sandwiches, right? And then Luke comes, and by the way, he texted me. He said, I'll be a little late. And so Luke comes, and he's 30 minutes late. He said, I am so sorry. I didn't have time to go to any stores, but we had a half a jar of peanut butter at my house, so I brought it. Okay, so now let's think about this. According to Ben, if you just look at Ben, he says, we're going to make hundreds of sandwiches. But then Luke says, we might make about 6. We might make 10, maybe. So what's going to happen? Are we going to make hundreds of sandwiches or 10? 10. Why? Because the peanut butter was the limiting reactant. And so in chemistry, whenever I tell you how much of each reactant I give you, or whether it's in grams or moles, a little bell goes off in your head. And you said, instead of 1 row of boxes, you're going to draw 2 rows of boxes. This is a story told through the eyes of the peanut butter and the story told through the eyes of the bread. Now, watch what I'm going to do here. Ready? I'm going to put a little asterisk here and right here. Now, what I'm going to do is I'm going to change grams of O2 into moles. Let's do that now. Change 100 grams of O2. And what's the shortcut? When you want to go down the mole world, what do? Divide by the molar mass. So here we go. What's 100 divided by 32?
3
What now? 3 point what? 3 point what?
125.
125? Okay, we'll do 3 sig figs. How about that? Is everybody getting that or not?
Pardon the interruption, please. Rhetoric student,
No.
quick announcement. If you are in the 8th, 9th, or 10th grade student council, or if you're on the dance committee, please stop by the student activity office as soon as you're dismissed from this class. And juniors, if you are serving, don't forget to come at 12 o'clock to the student activity office. Thank you.
Okay. Now, what we're going to do here is I'm going to forget. I'm going to forget about bread. I'm just going to say, as sold to the eyes of the peanut butter, what's going to happen here. Let's do some shortcut. Are you ready? 1. I'm going sideways, right? Gotta get bigger. So we're going to multiply by.
2 over 1.
I beat you. Is that right? So you got that in the calculator? And watch. Magic. Okay, you okay so far? Now it looks like this is how many sandwiches we're going to make. But wait, there's another story. I'm going to put a star instead of an asterisk here. And look now, I put this one down here. Not in the same row. I put it here. Now change that into moles. Down the mole world, divide by the molar mass. Whoa. Whoa. Man, that's a lot of moles. See that? That's a lot of bread, wasn't it? Woo. Okay. So now what? Let's tell the story now. Ready? Matchy.
Of course, Luke.
And let's go this way. You gotta get smaller. So you're going to multiply by what? 1/2? Okay, now, we are ready. I'm ready to tell you what's going to happen. Can you tell me what's going to happen? Are we going to make this many sandwiches or this many sandwiches?
That one. The other one.
Are we going to make 50? No. You know what? You're going to run out of this stuff first. Look at me again. You're going to run out of this. So see this? See that right there? That belongs to oxygen, doesn't it? O2 is the limiting reactant. Let's do it one more time. How did I know that? The bread says, I have enough bread to make 50 sandwiches, but the peanut butter says, we're only going to make 6. So what's going to happen? Who's limiting how many sandwiches are going to be made? This little asterisk right here, isn't it? Now, once you know who the limiting reactant is, watch this now. This story is going to happen. That story is not going to happen. We are not going to make that much. You get it? So here one more time. If they give you the grams of the moles of both reactants, you draw 2 rows of boxes. You tell the story both ways. Now here's another way of doing it. I'll show you a shortcut way of doing it. Ready? Say asterisk. I have that much peanut butter. I would need this much bread to use up all the peanut butter. But how do you know how much bread was brought? You go down here, right? I got way more bread than you need. Right, Dad? Don't call me the limiting reactant. I'm the one that's in excess. Okay, so therefore, you are the limiting reactant, and that's what's going to happen. All right, and when you get back